right, our lesson for today is the rational root theorem. So first I'm going to remind you of how we've handled these types of problems previously. We have factored completely, given a hint, because looking at this problem right here, where I have a function that I want to break down into the factors, I can't factor that. I can't factor this by grouping. So right now, I'm giving you a hint. X minus 1 is a factor, and if it's a factor, that means that as a solution, x must equal 1. So let me divide it out using synthetic division. So 1 is divided out, and then I transfer all of those coefficients. So I'm going to transfer the 1, negative 6, 11, and negative 6. Okay, bring down the 1 to start, multiply, add down, multiply that 1 and negative 5. Okay, 11 minus 5 is 6. Multiply that 1 and 6. Gets me 6 here. When we add down, we get 0. So remainder of 0, perfect. That confirms that x minus 1 is a factor, and that I would have an x-intercept on my graph of 1, 0, right? I have a solution at x equals 1. So now what's left over? Here, this is quadratic linear constant. So I have x squared minus 5x plus 6. So if I keep factoring this down, what multiplies to negative 6 that adds to negative 5, I should get x minus 2 times x minus 3. So now if I want to write out the full factorization, I have f of x is equal to that first factor that I divided out, and then I also have the x minus 2 times x minus 3. So fully factored, and then I'm able to see how I can graph that because I have an x-intercept at 1, 0, 2, 0, 3, 0, and I know that it's positive in cubic. So I know exactly how I would move forward and graph this. Okay, this next one, staring at it, again, I can't factor this by grouping, so I'm stuck. Here I'm giving you a solution at x equals 5. That's my hint, which means as a factor, that would have been x minus 5. So here I'm going to divide up that 5 and see what's left. So again, I'm going to transfer all of those coefficients. Bring down that 3 to start. Multiply that 5 and 3. So here's 15. When we add down, we have 20. Multiply the 5 and 20, get 100. Add down, negative 7. Multiply. Add down. Remainder is 0. Yay, as it should be. So now what's left over? Quadratic linear constant. Okay, keep factoring. This isn't a basic one though. This one's a little bit more complicated because of that 3x squared, but it has to be a 3x and an x. Now I'm thinking of how to get to that negative 7. I know it has to be 1 times 7. One of them has to be negative. So it makes sense that I have a 7 here because that will make a 21x. Here's a 1x. And since I want it to be a positive 20x in the middle, must have a 1 here and a minus here. So then if I write this function fully factored, okay, that solution as a factor would have been x minus 5. And then it's going to join the 3x minus 1 and the x plus 7. And again, I know how I could graph it, positive cubic, so I know the end behavior, and these would give me the x-intercepts. All right, but what happens if we don't give you a hint? Enter the rational root theorem. So given a polynomial function with integer coefficients in standard form, every possible rational root solution written as a fraction can be written in this format. So remember that rational numbers are just numbers that we can write as a fraction. Okay, we can write those possibilities in the form of plus or minus p over q. So all that is, p is factors of the constant and then q is factors of the leading coefficient. Okay, so here in example 2, I'm going to actually use that. So I'm saying find all of the possible rational roots. Well, right here, that is my constant, so that's my p, and then my leading coefficient is q. So I'm looking at plus or minus factors of 4 over factors of 12. So numbers that go into 4, well, 1, 2, 4, and then into 12, 1, 2, 3, 4, 6, and 12. So I'm looking at every combination thereof. This gives me a list of all of the possible rational roots. It's not going to give me anything that has I. It's not going to give me anything with a root, but it's going to give me all of the other options. So making my list, if I start with 1, 1 over 1 is 1. 1 over 2. So plus or minus 1 over 2. Plus or minus 1 over 3. 1 over 4, 1 over 6, 1 over 12. Right, already it's a big list. Okay, now looking at the 2 over 1, over 2, over 3, and so forth. I'm going to write that list. I don't have to write it if it's a duplicate. So 2 over 1 is 2, but 2 over 2 is 1, and I already have that. I don't have 2/3. 2/4, well, that is just 1/2. And 2 over 6, well, that's just 1/3. And 2 over 12, that is 1/6. I already have those represented. So now look at the 4 over each of these options here. So 4 over 1 is 4, so plus or minus 4. But 4 over 2 is 2, already have that one. 4 over 3, that's a new one. Okay, 4 over 4, we're back to 1. 4 over 6, well, we're back to 2/3. And 4 over 12, that's 1/3. So here's my list of all of the possible rational roots. And that's a pretty big list. All right, so now building off of that, now we're going to say, well, can you find all of the zeros? And sometimes we call those roots, and sometimes we call them solutions. So a lot of that language is interchangeable. So things to keep in mind. A polynomial equation or function will have the same number of zeros, roots, solutions as its highest degree. So something cubic should have 3 total solutions. Some of the zeros or roots or solutions will be real, some will be imaginary. Graphically, the real solutions are x-intercepts, and that's really what we've shown you at this point. First, we want to see if the equation or function is factorable, and if it is not, then we're going to use this rational root theorem to find all possible rational roots. right? That's the plus or minus p over q, factors of the constant over factors of the leading coefficient. Then we can use substitution, synthetic division, or log division to check. Remember that it is a solution. It is when the remainder is 0. Okay, then we would repeat the step above, or we'd factor the remaining polynomial. You may need to solve using square roots, quadratic formula, or complete the square. So if I can get it down into a quadratic, right, then I can drag it through the quadratic formula or use square roots or complete the square. All right, so here first up, use the rational root theorem to factor completely, then solve for all zeros, graph the polynomial function, label all x-intercepts and the y-intercept too. So let me slide that up. All right, so first up is just making my list of the possible rational roots. Remember that this is the p, this is the q. So if I'm looking at my list of possibilities, all right, so possible rational roots, I'm looking at plus or minus p over q. So here factors of 2 over factors of 8. So for 2, that could be 1 or 2, and for 8, that could be 1, 2, 4, or 8. So I'm looking at all of my different combinations thereof. So plus or minus 1 over 1, 1 over 2, 1 over 4, 1 over 8. Okay, with the 2, 2 over 1 is 2, but 2 over 2 is 1. I already have it. 2 over 4 is 1/2. I have that. And 2 over 8, that's 1/4. I already have that. So here's my list of all my possible rational roots. No other options besides those. So my hint to you is to try integers first. Okay, and you could use either substitution or you could use synthetic division to see if it is an actual 0. So let's say that I tried 1. Let's say I tried x equals 1. What I'm doing is I'm plugging it back into this function to see if the remainder is 0. So if I use substitution, right, I'm seeing what is h of 1. If I plug in 1 for x, does it output 0? So let me show you how I'm just plugging that in for x. And what it's going to output. So 8 times 1, 8 plus 10 minus 11 plus 2. Ooh, that's going to give me 9. So not a 0. It doesn't give me a remainder of 0. Let's keep trying things. Let's say I try negative 1. h of negative 1. What does that give me? 8 times negative 1 cubed. 10 times negative 1 squared. Minus 11 times negative 1 plus 2. So that would give me negative 8 plus 10 plus 11 plus 2. That's 15. Okay, not 0. These would be points on my graph. I'd have a point at 1, 9, negative 1, 15, but this is not where it crosses the x-axis. So I keep going. Let's say that I try x equals 2. Again, I said integers first. So if I show how that's plugging in first, I'm just plugging this in for x. Okay. So here that would give me 8 times 8, so 64. 10 times 4 is 40. Minus 22 plus 2. Way off, right? That's 84. Not it. All right, this one's got to work. Let's try x equals negative 2, and then I'm out of integers. So h of negative 2. So 8 times negative 2 cubed, 10 times negative 2 quantity squared, minus 11 times negative 2 plus 2. All right, so 8 times negative 8, so I have negative 64 plus 40 plus 22 plus 2. Amazing! I finally got 0. I need a remainder of 0. Now, some people would do synthetic division 4 times to finally get that 1, and then you have it divided out. I like to use substitution just to find it first, then I go and do synthetic division. So here, when I do synthetic now to divide out x equals negative 2, I need to transfer down all of those coefficients. Okay, and then I'm going to divide it out and see what I'm left with. So I bring down the 8, multiply, add down, multiply, add down, multiply, again confirms that my remainder is 0. So what I'm left with now is my quadratic linear constant, always 1 degree less than how the problem started. So if I carry that up here, I have 8x squared minus 6x plus 1. So here, if I want to keep solving so I can see all my solutions, I'm going to set that equal to 0, and I'm going to see if I can factor it. I hope I can factor it, and if not, then I probably take that to the quadratic formula. So here, I think it's going to be 4x and 2x. It could be 8x and 1x. Let me just stare at this for a moment and see if that works, because I only have so many options when this is a 1, right? It has to be a 1 and a 1, and they're both negative. So let me see if this option works. This would be a minus 4x. This would be a minus 2x. That's it. I found it. Amazing, right? The only other option to sort through for factoring would have been an 8x and an x, and that would not have worked. So I was able to factor that down really quickly, and when I solve, right, when I set each of these factors equal to 0, I would get my other solutions of x is 1/4 and x is 1/2. So writing this function here now fully factored, I have h of x is equal to. So remember that I was able to divide out x equals negative 2. So as a factor, that is x plus 2. These other two factors, 4x minus 1 and 2x minus 1, right there. So I have it in factored form. And then my solutions, I can say that x equals negative 2, 1/4, 1/2. Okay, and then if I want to graph it, right here I know that I have a negative 2, 1/4, 1/2. I also know that it's positive and odd degree. Okay, I can see that my y-intercept, if I go back to how it started, right, I can see that it's at 0, 2. Maybe I'll tuck that little detail here. Y-intercept would be at 0, 2. I could also plug in a 0 here and see what it outputs for y. Another way to deal with it, I'll just plot a point right about here. So now I'm going low to high to graph it all. And what we care about, of course, are that we see the x-intercepts in the right spot, the y-intercept as well, and the right end behavior. And then label each of those values. All right, that looks good. Let's flip it to the next page. Okay, let's do one more example. I'll just move a little faster this time. So here again, I want to make a list of my possible rational roots. So again, P here, Q here. So for my possible rational roots, plus or minus p over q. I need factors of 12 over 1. Okay, so here that would be a 1, 2, 3, 4, 6, 12, and 1 is easy, right? That's just 1. So here I didn't carry the negative with it because I'm going plus or minus anyways. So I'm always thinking of what p is right there. I'm just taking it as it's positive because, again, I'm looking at all the combinations plus or minus anyways. So when I build my list, right, 1 over 1, 2 over 1, 3 over 1, etc. So plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, plus or minus 12. All right, there is my list. And I would do it the same way, right? I would use substitution until I find one that works. And I would use also just substitution before I use synthetic to divide it out. So if I went through my list, I probably tried the ones, 1 and negative 1, until I got to x equals 2. So let's say we plug that in, right? Y equals 2 cubed plus 4 times 2 squared minus 6 times 2 minus 12. So here I would have 8 plus 4 times 4 is 16 minus 12 minus 12. And amazing, we found it. Remainder is 0. So we found our first solution. Divide it out. Okay, so again, I transfer the coefficients. I'm using synthetic division. So 1, 4, negative 6, negative 12. Bring down the 1. Multiply, add down, multiply, add down, multiply. All right, so I'm just, again, confirming that the remainder is 0. And I am also seeing, right, that this is what is left over. So now with what is left over, let me just slide it up. Quadratic linear constant. Okay, if I stare at that and I think, oh, can I factor that? Is there anything that multiplies to 6 that adds to 6? Oh, no, there is not. So how can I solve it? I can't solve by taking the square root because there's a linear term. So my choices are to either complete the square or use quadratic formula. You have options. I like to complete the square when that linear term is even. So that's what I'm going to do. I'm going to subtract the 6. Split that linear term in half and square it. So 3 squared is 9. So I have x squared plus 6x plus 9 equals negative 6 plus 9. Okay, if I keep going right in here, I now on the left have x plus 3 as a quantity squared is equal to 3. Okay, and now I can solve by taking the square root here and here. X plus 3 equals plus or minus the square root of 3, and then take that 3 away. Okay, so I'm going to have a pair of solutions at negative 3 plus or minus the square root of 3. So when I write this factored, I would say that y equals, right, I could divide out the x equals 2. So as a factor, that's x minus 2. And then here, this was what it was left as, right? I couldn't break that down. So I leave that as x squared plus 6x plus 6 when I'm writing it factored. My solutions are simply x equals 2. And we also have the negative 3 plus or minus the square root of 3. If you wanted to write those separately, I would be fine with that. That's not a problem. So now to graph it, I need to know what the approximations are for -3 minus root 3 and -3 plus root 3. So if I type that into the calculator, let me just write them first. I get these approximations. All right, so -3 minus the square root of 3. And I need -3 plus the square root of 3. So here I get about -4.73 and -1.27. I'm just taking it to the nearest hundredth. And then the y-intercept as well. If I just go back, I can see it right here. So 0, -12. Okay, so if I plot my points, so I'd say I'm going to write about here and here and here. Okay, and then here's my y-intercept. Low to high, right? It's positive and cubic, so positive and odd. So comes up, slices through, comes back up like that. And then here is the -3 minus root 3. This one was the -3 plus root 3. This one's at 2. Y-intercept is at -12. Okay. Last thing to do is do a little bit more with multiplicities. So looking at graphical behavior of polynomials at horizontal intercepts. So we know that when we have multiplicities, duplicate solutions, right? We've seen that when we have a p-value of 1, so not a duplicate, it's a single value, a single 0, multiplicity of 1. It just crosses through the x-axis. And we've seen double roots, double zeros, multiplicities of 2, where it bounces off of the x-axis. So that's actually true every time we have something that's even. So higher even powers, the graph still bounces off the x-axis, the horizontal axis, but the graph's going to appear flatter with each increasing power as it approaches and leaves the axis. So it just flattens out when you have a greater even multiplicity. And when we have a triple zero, so another odd power, like higher odd powers, it's going to still pass through the x-axis, the horizontal axis, but it flattens out with each increasing odd power as it approaches and leaves the x-axis. It has this kind of wiggle to it when we have x to the third, when we have something like here where our factor is a multiplicity where it's an odd power. So the third, the fifth, the seventh power. So to show you what that looks like, let's close out with example 4. So here we know that this is going to be third power, second power. So overall, it would be quintic. It would be to the fifth power. I have a leading coefficient that's positive, and this would be odd if it was to the fifth power. Right here, that means since it's going to be odd, it's going to pass through, but have a little wiggle to it with that multiplicity of 3. And here it's going to bounce because it's an even power. Right, that multiplicity of 2. So for my x-intercepts, if I make a list, I have 1, 0, but with a multiplicity of 3, and I have -2, 0 with a multiplicity of 2. Okay, my y-intercept, right, if I plug in 0 here, I have -1 cubed times 2 squared. So that's going to give me a -4. So as a point, that would be 0, -4. So here at -2, I'm going to circle that because I'm going to bounce there. And over here at 1, I'm going to have kind of this wiggle to it. It's going to pass through, but not kind of like we see it when it's a line. So I'm going to start low and high. Let's say I put the y-intercept there. So I'm going to come up, bounce off the x-axis, come down here, pass through, and then I'm going to kind of wiggle as I go back up. So right here, I see that I only have touching the x-axis right here at the -2 where it's bouncing, and then passing through here with a wiggle because it was an odd power more than 1, right? And the higher that degree is, right, the more of this little wiggle it's going to be. So here is -2, y-intercept -4, and here at 1. I'm just going to use that word, wiggle, right? That's essentially what happens when it's an odd power more than 1. Okay, lastly here, let's just do one more. So here I see a negative out in front, so I know it's negative. This is x to the first power, 4th, 5th, so that'd be x to the 10th power, which is even. Okay, here I see that this right here would be a place where it's going to bounce because it's to the 4th power. And here, a multiplicity of 5. Here it's going to pass through, but with a wiggle. And I do see another one here at x equals 0. It's just that it's not a multiplicity. So if I list my x-intercepts, I have the origin, right? I have the 1 right here, but no multiplicity. I have the -1, 0, but that one has a multiplicity of 4. It's going to bounce. I have the 2, 0, which is a multiplicity of 5. It's going to pass through, but with a wiggle. And then my y-intercept is just at the origin, right? If an x-intercept is the origin, so is the y-intercept. So it's going to pass through here. At -1, I'm going to circle that because it's going to bounce. And then at 2, remember, it's going to have kind of a little wiggle to it. All right, so it's negative even, so low, low. So I'm going to come up, bounce, come down, pass through. And as I come back down, I kind of have this little wiggle to it, just like that. Okay, here's a -1, here's 0, here is 2. Now, there's no real precision to the wiggle. It doesn't have to be perfect. I'm just showing you what it actually looks like. What is important is that you're showing the right end behavior, the right places where it bounces, and the right places where it passes through. So this is just a little extra layer to your understanding. You can have a multiplicity that's not just even. It can be odd as well. And what it looks like on your graph is this kind of silly little wiggle effect that we're seeing here and here. All right, have a good day.